All right, welcome. So this hopefully will be a review session for most of you. We're going to do a really simple, basic circuit analysis problem, but we're going to do AC circuit analysis because that's the focus of our class. And then what we're going to do is I'm going to show you how I will solve it with my calculator, which I'm going to do it with MATLAB. And I'm not turning people into MATLAB experts. I'm just giving you some basics of how to do a couple of kind of useful commands in AC circuit analysis. So yeah, pretty simple stuff. So let's take a look at a simple circuit. And we're going to have a voltage source here. And it's going to be 7,200 volts. And the angle is going to be 0. So if you remember from AC circuit analysis, you have a magnitude and an angle for voltages and currents, okay? That's what's important and very different than DC because DC is just the magnitude only, right? Where for AC, when we do steady state circuit analysis, we have to make sure I'm recording, yep. We have to make sure that we understand there's a magnitude and a phase. And that's one common thing that people in this class, and when you do AC circuit analysis, you only talk about calculating the magnitude. So when I say what's the voltage of something, you should say the voltage is 7,200 at an angle of whatever that is. Same thing for current, okay? Those are the only two that should really have magnitudes and angles. You can obtain magnitudes and angles for other elements, but it's not exactly the same thing. And we'll talk about voltages and currents as phasors as we get into the material. Again, this should be a review, so I'm not covering anything that perhaps is known. So let's start with a pretty simple circuit. And we're going to put a resistor in here. And we're going to put in a 1K ohm resistor. All right. So we're going to calculate the current that is being supplied to this load. And the other thing, yes, sir?
Just double check that number is 7,200.
7,200, yep, at an angle of 0. Okay. And the other thing is when we talk about AC, we try to use uppercase letters, depending on where or how you're taught circuit analysis. Most of the time domain stuff we do is lowercase v, lowercase I, even lowercase p, perhaps, maybe another term. But over here, we're using uppercase to indicate that it's steady state or AC. So we can use Ohm's law, which will start off with V equals IR. And we're going to solve for our current. Okay. Simple calculation. Now, if you're dividing complex numbers, magnitude and angle, okay? The way that you divide complex numbers is you divide the two magnitudes just like you normally would do. And then you subtract the angles, right? You all remember that from doing maybe MAT228. I know in circuits and AC circuits, we do it differently. But in 228, do they do two-dimensional vector multiplication and division? You may have done that in pre-calculus. I don't know. I don't know how much people do with vectors previously to Calc 3, but this actually is a pretty easy calculation. So the way that we're going to solve for that, and I'm going to write that out. That's the magnitude. And the angle is 0 minus what? What is the angle associated with the resistance? 0. If it's not specified, right? In the case of resistors, it is specified. We know it's 0. But in most cases, if we don't know what it is, we can go ahead and put a 0 term in there. If you have an ability to know what it is based on previous knowledge, and we'll see that when we start looking at capacitors and inductors, we can't put a 0 in there. But resistors is 0, so 0 minus 0 is equal to 0. So you have 7.2 amps at an angle of 0. Right? That's our first basic circuit. We didn't even need to use a calculator, right? Because most of us can divide 7,200 by 1,000 in our head. Not too bad. Now let's add something to the circuit. And we're going to add what would be the equivalent of a motor. Okay. And a motor is going to have some resistance and some inductance. And I'm just putting these circuits in series. In reality, we'd only put them in parallel, but I don't want to have to do series parallel combinations. I know that that can get a little bit confusing at times. I'm really just trying to get through the basics of AC circuit analysis. So we're going to pick this resistor. And again, it may not necessarily be, equivalent to how you would normally size a motor load, but we'll call that 500 ohms. And we'll say that the inductance is 200 ohms. Okay. So everything in AC circuits, all the resistances, inductances, and capacitance have been converted to ohms. So this one we already know is an ohm. 500 ohms is a 500 ohm resistor. That 200 ohm inductor is there. Now, here's the thing about inductors. How much real power does an inductor consume?
0.
0, right? Why is that? What's the job of an inductor?
To store energy in the form of magnetic.
It creates a magnetic field and it can store energy there, but it doesn't really do that, right? Because you have to have a constantly changing current to go ahead and get that changing magnetic field. So sometimes it's storing it, sometimes it's discharging it. It's not like a capacitor. Nobody I know is going to raise their hand and say, hey, have you bought an inductor, go store magnetic field? Doesn't happen, right? You can't buy inductors to store energy in a magnetic field. Capacitors you can because they can store it, but in inductors, you can't store energy. Why is that? Because it's LDIDT is the voltage across it. So it's the rate of change of current. Once the current is not changing, meaning there's no current going in and out, there's no magnetic field, right? It goes to 0. So it's not like in a capacitor where you're integrating the amount of charge that goes in. This I'm just differentiating. And since I don't get a changing current, right? If I take it out of the circuit, there's no current through there. So it's actually not going to work too well for us. And in fact, if you take an inductor and you pull it out of the circuit, what's the potential that you could do? What happens if I take an inductor that's been charging, you get a varying current there, and you pull it out and you try to take it someplace else? What happens?
It has no.
Once I take it out, remember it's LDIDT. The current went from, let's say, 5 amps to 0 amps instantaneously. What is LDIDT equal to when you go from 5 to 0 instantly? What's the derivative of the change in Y over the change in X? It could be positive or negative, it doesn't matter, but it's going to generate an absurdly high voltage, isn't it? So as soon as you open up that device in an inductor, you actually can get an arc. You can generate crazy high voltages. You could damage equipment. A lot of electricians have been electrocuted in the field because they've open circuited inductors, essentially. So that's the other reason why you don't want to use an inductor to store energy, because you can do some real damage without even realizing it. So because this is a 200 ohm inductor and not a resistor, I can't just call it 200 ohms, can I? I have to add the J term there, don't I? Otherwise, when I do Ohm's law, I would add up 1000 plus 500 plus 200. That ain't going to fly, right? Because that's not a 1700 ohm equivalent resistance. It's a 1500 ohm equivalent resistance plus J 200 ohm equivalent impedance. So my Ohm's law is still applicable, but I'm going to tweak it a little bit. Remember how I called it I times R? In circuit analysis, we don't call it I times R. We call it I times Z, where Z is now called impedance. It's not called resistance. It's called impedance. Okay. And is Z in this circuit is R total plus, we'll call it JXL, whatever that equivalent motor load is. So that's going to be equal to 1.5K plus J 200. So my current, sorry, is equal to my voltage. That hasn't changed. It's still 7,200 volts at an angle of 0. But now I'm dividing it by 1.5K plus J 200. Now, depending on your calculator, this could be really easy to enter and calculate, or it could be very difficult. The TI-89s can do this pretty easily, but I know something even easier. That's called MATLAB. Just going to use MATLAB to do this calculation. So in this case, I'm looking for current. So I know my voltage is equal to 7,200. Anybody know how to enter 0 as 7,200 at an angle of 0 into your result here? It's just 7,200, right? 7,200 at an angle of 0 is 7,200. It's a vector that lives on the x-axis, right? So that's easy. Now to enter z, this has got to be a vector that includes a real part and an imaginary part. How do we enter that in? 1,500 plus J 200. Okay. Hopefully not too bad. I hit enter, and then it just copies, MATLAB copies it down. Now I'm going to calculate I is going to be V divided by Z. So my current is 4.72 minus J 0.63. And that's my current. All right, so your boss said, go ahead and calculate the load with the addition of this motor. And you said, I did a great job. I deserve a raise. I came up with a current of 4.72 minus J 0.63 amps. So you're ready for your raise, right? And what does your boss say? Huh? What is that? I don't care about that current. I care about magnitudes and angles. In AC, we do magnitudes and angles. Anybody want to guess as to why? Why do I care about magnitudes and angles? When you buy a piece of cable or conductor or wire, what is it rated on? It has an ampacity, doesn't it? So if I buy a 777 KC mil cable that's good for 1,200 amps, would this cable work? Well, it's pretty low current, 4.72 minus J 0.63, but I don't know the magnitude of that. So I want to get the magnitude of the current. And since you're all wonderful at math, I know this is your preferred way, right? You're going to go ahead and do this. You're going to say, all right, I can do Pythagorean's theorem. That's my magnitude. And then my angle, no problem. It's negative inverse tan. Oops, I put the point in the spot. I can get the angle, right? SOHCAHTOA? No? Is that confusing how I got that angle? If it is, say yes. It's no big deal to show you. Everybody understand? So if I put this on a test, they'll be able to give me angles just by looking at this. One person's brave enough. So this is my voltage, my current down here, right? This is at an angle of 0. So it's 7,200 at an angle of 0. How do I get this angle? Well, I know this is 0.63 and this is 4.72. So can I SOHCAHTOA it? Sine, opposite over the hypotenuse, cosine, adjacent over the hypotenuse, tangent, opposite over the adjacent. Isn't the opposite here? and the adjacent here. We do a lot of trig identities in this class, but we love right triangles in this class. So you're all welcome to do that. I'm going to use MATLAB. And I'm going to say we'll call it, I just like to use the term display. That's going to be, another way to say magnitude is the absolute value of I. And if I want the angle of I can go ahead and put the angle of I. There's one problem. MATLAB only works in radian mode. There's no such thing as degree mode. So if I want to go from radians to degree, what do I need to do? Multiply by 180 over pi, right? So I've got 4.7579 at an angle of minus 7.6. That doesn't look real good. So I'm going to modify that and I'm going to put brackets around there because once I put brackets here, MATLAB is going to identify this as an entire number. Okay. So it's going to put them in both in the same row. That's the magnitude and the angle of the current. 4.76 at an angle of minus 7.6. I have a question for you. What does Eli say about this? Everybody's like, Eli? Who's Eli?
Yeah.
Anybody know who Eli the Iceman is? You can say no.
No.
I like to be non-gendered, so I just call it Eli the Ice. Everybody here has had some AC circuits, right? I actually have to do it over here because I got people in TV land. So Eli the Ice. What this tells me, L is an inductor. And I see the current, the voltage first before I see the current. Another way to say that is the current has to lag the voltage. Isn't this lagging the voltage? Everybody understand what the rotation is for a sine wave? Any general sine wave? It is always counterclockwise. Probably were taught that in physics back in the day, but you always have counterclockwise rotation. So if I put my eyeball over here, the one I see first is voltage, and then the current is next. And it's never going to be like, hey, why can't the current be first and then the voltage? Because they're always going to be leading or lagging each other by 90 degrees. You can never have a voltage or current that's leading or lagging by 200 and, well, let's say 190 degrees. You can't get a real world circuit to do that. Okay. So it's always going to be in quadrant 1 or quadrant 4. All right. So what we did in MATLAB was to show you just a really simple calculation, just like you would with your TI using the value of I. Now let's go back to our circuit and say, well, I don't want to put just an inductor there. I want to go ahead and I'm going to try to fix some problems that motor causes. And I'm going to put in a capacitor in here. And that capacitor, I've only got one on the shelf. Oops. Still need my equivalent motor circuit. So that's J200. This is 500 ohms. And I'm going to put in a J500 ohm capacitor. But a capacitor doesn't have a positive J term. It has a negative J term. And that might make more sense to you if you think about LdIdt versus CdVdt. And if you think about the phase shift that is created, you might start to see where that kind of gets in there. But once you start looking more at the sine waves, it'll hopefully make a lot more sense. So now I'm going to do my calculation all over again, and it's exactly the same process. It's going to be V divided by Z is going to be equal to my 7,200 at an angle of 0. And I'm going to divide that by my Z. So the way that you do that is you add up all the resistors together, all the real parts, 1.5K. And then I add up all the imaginary or reactive parts. I've got a J200 and a minus J500. I just add those together, including the sign changes. And there's nothing wrong with adding that negative value. So it looks like I'm subtracting them, but I am in fact adding them. So J200 minus J500 is negative J300. Okay. So now I'm going to tweak things just a tiny bit. I'm not going to go to MATLAB and have to type that stuff again. I'm going to go ahead and do a script file. And you don't have to do this. This is just a way of making things a little bit more efficient for you when you write MATLAB code. Like say you're going to do 10 problems and they have a similar format. Instead of typing everything manually like you would have to do in your calculator, I'm going to go ahead and write the voltage. Then I'm going to write the value of Z, which is 1500 plus J, and I got to do the time, J times negative, or it's actually minus times 300. And then my I is going to be equal to V divided by Z. In MATLAB, the semicolon, all that does is it suppresses printing what is on your screen. So you know all these things here when it had answer and all that stuff, it's not going to show you what the answer is. And the reason why I don't want to see the answer is because I really just need the magnitude of the current and the angle of the current. So now I'm going to display my value of I using the matrices and the absolute value and the angle. So that's the open bracket, absolute value of I, can't type, and then the angle of I multiplied by 180 over pi. And so now that I have the script file, that's great because I don't have to do that anymore. I can just keep reusing that script file. So this is the advantage of MATLAB. Whenever you use your calculator, you have to type it in brand new every time. Well, in MATLAB, once I save this script file, I can use it time after time after time after time. So I'm going to go ahead and save this. And for what it's worth, I just use the MATLAB editor and I'll show you why. But all it has to do, you just need a text file, a .txt file. So it's ASCII text. So if you want to use Notepad, you're welcome to use Notepad. You can even use Word if you want, as long as you follow the syntax. And when you save it as an ASCII text file, it'll work perfectly fine. So I'm going to save it here and I'm going to say AC circuit demo. Now the file type, the file name is important. You can't start off a file with a number in MATLAB. It'll give you a problem. So it has to start off with a character, and they're kind of specific about what characters you can use. Like you can't use a plus sign or an ampersand sign in there. You have a lot more flexibility in standard Microsoft. In MATLAB, it's a lot more limited. So stay away from goofy characters. If you need spaces, because a space is not a valid character in MATLAB, you can just use the underscore sign. Do not use the period sign or the semicolon sign or colon sign. Those mean very different things to MATLAB, but the underscore doesn't have any problem. So you can see I'm saving it as a MATLAB file. Now I'm going to go ahead and run it. Change my folder. And it gave me 4.71 at an angle of 11.31. Okay. So let's go back to Eli. So it's 4.71 at an angle of 11.31. Is our friend Eli the ice satisfied, or are they dissatisfied with our work here?
I don't understand your Eli yet. You explain that again?
Sure. So the key thing about Eli the ice is the middle letter. An inductor is represented as an L. Okay. In all circuit analysis classes, I'm hoping everybody has referred to an inductor with the letter L as Henry's. Typically, anybody seen it differently? Always L. A capacitor is always a C. So the middle letter in Eli the ice is the defining type of circuit that it is. So in the first circuit, it was a resistive inductive circuit. So it had some resistance and some inductive. So that would mean it's more inductive circuit. So it's going to fall under Eli because in an inductor, the voltage presents first and then the current comes on. And that has to do with the sine wave. Okay. In the second case, I put a really big capacitor greater than the 200, the 200 that I had for the inductor. I'm actually canceling out the fact that there's an inductor by putting a much larger capacitor. In fact, it's 300 ohms magnitude larger than the inductor. So that circuit becomes more capacitive. And how do I know it's more capacitive? Because that is a negative number. So once I know it's a capacitive circuit, then I'm going to focus on the ice part of it. And in a capacitor, what comes first, I or E? I. So in a capacitive circuit, the current presents before the voltage. Okay. So Eli the ice is just a kind of a mnemonic that'll help you, like, are my values what I expect it to be? Should I be getting a plus here or a minus here? Well, looking back at my diagram here, here's my voltage. That hasn't changed. Now my current is someplace up over here. So in an ice circuit, which means it's more capacitive than inductive, so the capacitance dominates, is my diagram that I have here showing my V and my I consistent with what my ice tells me it should be?
Yeah.
The current presents before the voltage. So if I rotate in a counterclockwise direction, I see I before I see E. So that checks out with my ice. Yes, sir.
Why is the voltage here represented by the letter?
Oh, that's just because it works that way. Instead of saying Bly and Bzis, or however you pronounce it, we just call it Eli the ice. If you go back to physics books, and you all can comment on this, some people use E for voltages, right? If I really want to throw you for a loop, you know what they use in Europe? They use U for voltages. But in the US, I think all of North America, I think Canada as well, they typically refer to voltage with the letter V. But I think physics technically, if you look at some of your early physics books, they would say E is equal to something. That's like the base level physics. But just like current, like the letter I is the square root of -1, right? Why don't we use the square root of -1? Or I for the square root of -1? Because I is current. We use J. And because I is so commonly used, if I go to MATLAB, I type in I, square root of negative, it's just a square, it's -1, right? Oh, or J is the square root of -1. It's -1, right? So you can see that I or J are already predefined in MATLAB. I didn't redefine it. I could say that J is equal to 32. Now when I type in J, that's gone. Right? I don't want to do both though, because if I said I was equal to 32, then it would screw up all my results. So I got to be careful about reassigning my complex number. Again, I encourage you to use the J term in here, just because if you use I and I, sometimes I is a complex number, sometimes I is the actual current, you're going to twist yourself into knots trying to figure out what I did I actually mean. So if you just use J, you know that that's the complex number. And I know that can be a little bit confusing for electrical majors, but that's just unfortunate. We only have so many letters that we can work with. Okay. So now I have a script file, and the best part about my script file is, let me zoom out a little bit. I actually have a debugger in here. So you know when you do your calculator and you're getting an answer you don't expect, what do? You go back line by line to figure out what the mistake is, right? Over here, I can do that manually. So first thing is, let's say that I forgot to put a bracket here. Look what happened. MATLAB gave me a red line. And it shows me where that red line is. So I can see the debugging built into the MATLAB editor is telling me there's a problem there. So if I try to run this, it's going to give me a beep noise. And it's not even going to be able to run it. And it tells me there's a problem in line 4, column 33. So I can't even run this file. If it runs, but I'm getting goofy results, then what I can do, and this is a really simple program, so it's easy to debug. But if you decide to use MATLAB and you want to use later calculations, I actually can set a breakpoint here. And you'll notice, oh, how come the breakpoint didn't get set? I don't need that. Sorry. The wrong button. Right, so now I'm going to run. And you can see it stopped at line 1 in the red. And so it's ready to process this line. So if I go back over here, nothing happened. Now I'm going to step into the line. Now it's gone. And now I can see I got 7,200. So it gave me a result. So now I can sanity check. Should I have gotten a voltage of 7,200? Yes, no. Then continue debugging. Okay, let's go to my next step. That's my impedance. Does it match what I originally calculated? This is obvious. It's 1,500 minus J300. You can see it. It's kind of screaming at you in the face. But if I entered in an incorrect value, or if I did my calculation incorrectly, then I can check and see that I'm getting goofy results. And then you can go on and on and on and do the whole process. Okay. You clear all the breakpoints and stop the debugging. So again, that's the basics of being able to troubleshoot something in MATLAB. All right, let's change up the problem. Here's my problem here. So I'm going to do that exact problem all over again. I'm going to have 1K ohm. I'm going to have 500. I'm going to have J 200. And my capacitor is minus J 500 here. So remember we talked about the concept of the load dictating, a lot of the different things. What if I have a mandate that this must be 7,000 volts? Because I'm connecting my expensive load to your system, and I'm only going to do that if I'm fairly confident that you're going to give me the 7,000 volts that I expect. Now, I'm going to have a transmission line, and let's say that that's 100 ohms of impedance. And I'm going to have a voltage source over here that the utility is responsible for providing, right? Because they're providing the load. And that is adjustable because I'm mandating that I want 7,000 volts there. So how would you calculate what, let's go 7,000 at an angle of 20. Let's make it a little more challenging. You would never have the 20 in there, but I want to show you something specific in MATLAB. So if I have 7,000 at an angle of 20, I need to solve for what does V source need to be. Okay. So the first thing I'm going to do is calculate what the current is at 7,000 volts. So just like we did before, my current is going to be equal to 7,000 at an angle of 20 divided by my 1,500 minus J 300. That's my current going into the load. Now I need to include the voltage drop across the transmission line, right? Because we know that that current is a series current that runs all the way through. And that's going to give me a voltage drop. And my source voltage is equal to my line drop plus my load drop. Okay? And how do I get my line drop? Hopefully you see that. That's just 100 or I times 100. That's V line. That's the voltage drop across the line. Now, I need to know what my load voltage is. That's 7,000 at an angle of 20. Okay? So now I'm going to go ahead and do this in MATLAB. And I'm going to save this as a new file. And we'll call this demo 2. This is our second circuit. And so my voltage now is no longer 7,200. It's 7,000 at an angle of 20, correct? All right. How do I enter angles in the MATLAB? I can enter complex numbers, right? I can do 3 plus J4. I've done 1,500 minus J300, no problem. How do I enter in magnitude and angle? I don't know, you tell me. Can I do this? Does that look like angle? Want to try it? I got nothing. 7,000 less than 20 is a logical condition, right? It's asking is 7,000 less than 20. So when I look at my voltage here, see, it's a logical 0. That's not what I want. I want 7,000 at an angle of 20, not 0. So that didn't work. So what am I going to do? I can't do 180 over pi because that's rectangular coordinates. I need to do things in polar coordinates. So everybody loves math, so go ahead and do a tan of the complex part over the real part. That would work, wouldn't it? But it's work. Remember, engineers are lazy. I mean, efficient.
Yeah.
So what's a better way to do it? Who here has a math minor or signed up for a math minor? Can I pick on you?
Sure.
Tell me the answer. How do you enter complex numbers with angles in them?
I don't know if there's a more direct way to do it. You could do the cosine of the angle times the magnitude for the real part, and then add on a J, and then the magnitude times the sine of the angle.
He's on the right track.
Be you doing it, but I don't know if that's the most efficient way.
You're on the right track, but you're making it harder than you need to be. So you're right, it's not the most efficient way. What was the term? What term would you describe if you just did?
I don't know.
No, the math. What specific theorem or identity did you use to get that? Euler's or Euler's identity, right? What's that? No, sine or cosine wave is a time domain varying thing, right? Sine of omega t plus theta. Isn't that what an actual sine wave is? Sine wave is different than a sine of a function. Sine wave is this. So you can represent it mathematically, but you have to have the time to be able to calculate that, right? But Euler's or Euler's identity, depending on who you ask, is M cosine theta plus J sine theta, which is equal to the real part plus the imaginary part. So you use Euler's identity to enter any complex numbers. In MATLAB, M e to the j theta is 7 times E, which is exp, times J times theta. But 20 degrees is not 20 radians. So I have to multiply that by pi over 180 to convert to radians, correct? So if you're going to use MATLAB to enter complex numbers, you need to memorize how to do this. This is the only way, only efficient way, I should say, that you can easily enter in complex numbers in MATLAB. It's using Euler or Euler's identity. Right? So it's M e to the j theta. You put your M there, 7,000. You put your E for 20, and then you multiply by pi over 180 just to go ahead and do that. All right, so let's put these back in. Whoops. So I got my I, and if I want to display my I can, but I really don't need it. So now my V source is going to be equal to my line voltage drop, which is just going to be equal to my I. Is it I display or I just my value of I? Should I multiply 100 ohms by I display or I? I. Don't multiply it by I display because MATLAB can't handle magnitude and angles. It doesn't work that way. It can only multiply real and reactive parts. It can only multiply in rectangular coordinates. So I multiply I by 100, but again, it's going to be a complex number. So I want to display my voltage. So it's the absolute value of the source and the angle of the source times 180 over pi. Okay. So now I'm going to multiply that and run that all out. So I clearly did something wrong because I've got 457.
Why didn't V4 now divide times 10 to add the 7,000?
Oh, plus 7,000 there. So I didn't calculate V source. I calculated V line, right? Very good. So I'm going to add to that V, right? That's the original voltage. Now do my calculation. And here's the problem with using everything in the same matrix. I'm getting 7,450 volts. And my angle is pretty darn small, isn't it? So here's the problem when you do everything combined. You can see that when I'm dealing with thousands of volts and my angle is 20 or 15, it kind of gets lost. So when you're dealing with big voltages, what I suggest, one of two ways. Divide that by, if it's a kV, just divide it by 1,000, or separate the magnitude and the angle calculations. So here I'm going to divide it by 1,000. I'm going to run it, and you can see that I get 7.45 kV at an angle of positive 20.69. Okay? And that's how you would do some pretty simple calculations with MATLAB. I didn't do anything really seriously difficult, but what I wanted to show you is a little bit of syntax with MATLAB. It takes a little more time to enter things in, but you know how you all do calculations on paper? I did all my calculations here, right? I didn't have to do anything on the on paper and then transpose it to the calculator. I can see everything there. And then the best part about it is, as he pointed out, I forgot to include the source, the voltage across the source. And you could see, oh, I missed that. So now I just add it in there and you can see it there plain as day. Another nice thing about MATLAB. I can add comments. with the percent sign. So instead of having a separate piece of paper and a calculator, I can include comments actually in my script file to provide lots and lots of detail. So I can have simple ones, or it'll keep adding characters, right? Until you can't print it. So what I'll do is maybe I'll stop it here. Then I'll hit a character turn, and MATLAB is smart enough to put the parenthesis there. And you'll notice the text is green, right? So I'll do another one over here, keeps it green. And then you can even see some information over here that MATLAB, if I wanted to truncate it and shrink that, I can go ahead and minimize it. I also, if I want to go ahead and do the debugging thing that I had, so if I set a point here, if I run that, see the arrow? And then if I step to the next one, watch what happens. Skips right through the comments because there's no processing necessary by MATLAB. So you can skip right through the comments. So again, just a nice feature that you can put yourself some information that you want. Last thing I'll show you with this simple example. I've been doing a lot of work, right? My screen has a lot of gibberish in here. I may not want. So I can type CLC and it just is going to clear the screen from information. I can still see that I have a voltage in here, right? I didn't clear the variables. I just cleared the screen. If I want to completely clear this stuff off, I type clear and watch what happens to the variables on the left. Gone. So now if I type V, it doesn't know what V is, unless it's a built-in variable by MATLAB. So if you want decent looking script files at the beginning, I just do clear and CLC. I will do clear on all my equations in MATLAB that I do in the class, because as I tell everybody in my classes, I want to be honest. So if I give you a result in MATLAB, and it's on if it's on my PowerPoints, and you'd be like, how did he get that answer? There's no way he could get that answer. But by doing that clear up front, sometimes professors are kind of clever and they'll put the answer they want at the beginning of class and you don't even see it. And then it just happens to work out. And you're like, oh, how'd they get that answer? But with MATLAB, if I clear all the variables, I don't have that luxury. So the answer that I have should match what's on the screen. And if it doesn't, there's either an error on the screen or an error in the MATLAB file. And that's going to be a lot more useful when we get further along, when we have to do iterative approaches. So when we look at iterative approaches, you can actually see, are the results valid? And we work through that. You don't have to do the clear and the CLC. That's totally up to you. Another nice thing about MATLAB, if you haven't been convinced already, is I can do a publish feature. And it's not great for publishing, but it does okay. So I can actually publish this, and I'll show you this in a second. So this is my output folder, but I can change it to a PDF. And I'm going to publish it, and let's look and see what MATLAB does. Should bring up the PDF file in a minute. Why isn't it bringing it up? Oh, there it is. Oops, maybe because, maybe because of breakpoint, it's giving me some issues. Oh, it just took a second. So this is what you hand in for your class. It has your work, you know, like your scratch paper work, and then it has your results that you want to display. So instead of having to manually write things in and do it all on paper and go back and forth, if you set it up in MATLAB, you have everything right there. Okay. Again, not the greatest, but it does a pretty good job of showing you the script and as well the answer. Because I want to see both. I want to see this. And I actually am more interested in seeing your comments. Because your comments are actually where you explain it to yourself, and then hopefully that makes sense. And then this other stuff is just the actual implementation. And then I like to check the results just to make sure it's a reasonable approach. Because with almost 50 students in the class, you know, grading is going to have to be pretty limited to be able to grade, because, you know, unless you never want me to do anything else but grade, forget about teaching, but just grading the whole time. So super duper useful. Okay. Don't have to use MATLAB, but it's got a lot of useful features. And when we start to do iterative approaches at the end of the semester or towards the end of the semester, MATLAB has a while loop capability or for loops. So you can just iterate through. And it's just like standard while loops. It's just while something is true, do the following. Most of us have had at least some computer programming, I think, right? Like if I say do while loops or for loops, it doesn't scare people. There's no if then. You can set it up. You can do if then, but we don't have to do that. Makes it easier then. Okay. All I had on my agenda to try to cover today, because we haven't covered any more material. Any questions on this or anything in the class or whatever? Our next lab will be a little more with new material. This is just hopefully review. Yes, sir.
Sorry, I was wondering where the button or what to go to get the PDF again.
The publish, sure. So if you go to publish here, see it's highlighted here. I click publish, then I click publish over here. I always will edit to make sure that I want, you know, that I get the right output that I want. And then I will publish that here. But it has to be a working script file. You can't get a publish file because it actually is calculating your output. So you see that it was getting me my voltage and my current. And the only way it's able to do that if it can run through the script file without error. So if you have errors, it's not going to run. This is only for your final product. Makes things very, very efficient.
Thank you.
Yep. Other questions? Ah, where do you get MATLAB? So if you're on campus and you have a Main Street account, so I'll just go to Edge, go to umain.edu. Oops, I should have done one more step. /IT, UMain software. There it is. Has anybody else downloaded it in the last week or so? Have they tried? You just download it now?
Well, I don't really want to go over there.
Okay. Did anybody download it prior to class? It doesn't take a long time to download if you're on campus at 1 gig speeds. But if you're off campus, depending on your speed, it does take a fair amount of time to install because again, it's like 5 GB. So it's a pretty big file. So also make sure that you have sufficient room on your computers. But yeah, you get it for free if you're on campus student. Other questions?
This one doesn't, my question doesn't have so much to do with what we did in class today, but you know where they did the new Route 9 cutover in Brewer?
I know of it, yes.
Those transmission lines there, it looks like there are 2 lines per phase. Do you know why they do that?
Yes, I know why, and you will know why once we cover transmission lines. I can tell you that's called a bundled conductor, and it's usually for only voltages for 345 kV and above. But I can't exactly tell you. I mean, I can tell you why. It has to do with decreasing the amount of inductance and increasing the amount of capacitance based on the conductor spacing. But I don't know if that makes a lot of sense at this point.
Okay, cool. Thank you.
But yeah, you use bundled conductors all the time on transmission lines, but only for pretty high voltages. It doesn't make sense to run bundled conductors on lower voltages because there are other problems to doing that. All right, any other questions? Yes, sir.
the lab report for this lab.
Yep, I put up a lab report format. And I put that up on the labs folder. So it should be there. It's not going to be long-winded things. It's more about, efficient writing the process and coming up with just some details. So what I'm looking for is, can you explain to me how you did the lab? I don't need books and books and books of material. I just need you to go ahead and whatever process you did in the lab to understand it, to tell me that. That's all I need. Anything else? TV land? Okay. If not, have a wonderful day and I'll see you all tomorrow. Take care, everyone.